How about lower side? On the lower side, let's imagine the same pressure, right? You have P infinity, you have P infinity plus a delta P, P infinity minus a delta P prime, and back to P infinity. Again, this is a shock, right? And this is an expansion. This is another shock. As the velocity goes horizontally, what is the force? What is the direction of the force? We're going to see that the direction of the force is again going to be perpendicular to the contours, right? So this is the pressure force. However, the direction of the pressure force is different because the waves are aligned in a different way. So because the direction of the force is different, the response of the velocity is exactly the opposite, right? In the x direction is the same, but the angle is going to be exactly the opposite, right? You see that? Okay, if the velocity slowed down in the orthogonal direction and kept the same in the tangential direction, the velocity would curve downwards, right? And here, through the expansion wave, we have acceleration in the normal direction. The pressure would curve upwards, right? Exactly the opposite from on the upper side. And then goes horizontal again. Is this why supersonic airplanes are typically symmetrical or zero camber? Yes, but like let's look at that a little bit later, because what we are going to see is if you add camber, okay, if you add a camber to the supersonic airfoil, you're going to be reducing the pressure perturbation on the downside of the airfoil while adding pressure perturbation on the upper side of the airfoil, right? And then the critical thing about adding and decreasing pressure perturbation is to think about how does the drag respond to a change in pressure perturbation. If you change the amount of bulk, right? So let's say just to focus on the upper side. If you're increasing the maximum point over here by a factor of 2, as we said, the pressure responds linearly to slope in this region, in the limit of small perturbations. How would the delta P change? Increases by a factor of 2, right? But then how would the drag change due to the pressure change? Okay, the drag is the force component in the downstream direction. Okay, and the pressure here, right? It has a small component pushing the airfoil downstream. The pressure here is negative, right? Think about the delta pressure here is negative, so it kind of pulls the airfoil in this direction, which is again a little bit downstream, right? That's the source of the supersonic wave drag, is the increase of pressure in the upsloping region and decrease in pressure in the downsloping region. If you increase this by a factor of 2, not only does the pressure, delta pressure increases by a factor of 2, but also the slope increases by a factor of 2, right? How much does the drag increase as a result of that? Again, let me reiterate. If you increase this point by a factor of 2, so let me just draw some dashed line. Okay, here would be plus maybe a factor of 2, right? I don't know how to say that, but like the delta P would increase by a factor of 2. The delta P prime would also increase by a factor of 2, and the original slope becomes that. Okay, so even if delta P is the same, the component of the pressure force in the downstream direction is increase by a factor of 2, right? So by the way, this is in response to the to the question, why do we want zero camber? If you increase the camber, let's say to the same as the half thickness, that basically makes the bottom flat and increases the top by a factor of 2. Okay, you eliminate any pressure perturbation on the bottom, which makes the bottom not contributing to the drag anymore. But the top is now contributing how many times the drag? Again, the pressure delta increases by a factor of 2 and the slope increases by a factor of 2. What's the resulting drag increase? Factor of 4, right? Okay. Is it clear, or what's the muddy point about this? Yes?
Will you explain again what increasing the top surface does to the bottom surface?
So let's compare two designs. Okay. So one design is a symmetric airfoil. Let's make it simple, just to say the same thickness and with no camber. The other foil is same thickness, but so still T, right? But have a camber that's equal to half T, so that the bottom is exactly flat. I'm exaggerating here. Usually you don't make such thick airfoils for supersonic flows. But now this angle here, right? Let's say theta is now the same, twice as big as the theta here, right? So the delta P here is going to be twice, let me just say 2 delta P. The delta P here is going to be twice as the delta P before, right? And let's say for a symmetric airfoil, this is minus delta P and this is minus 2 delta P. And here you have delta P, and here you have minus delta P, and here you have 0 and 0, right? Okay. So the amount of drag you contributed can be computed by delta P here times half chord, right? And of course times the span. I'm just saying the drag per span. Then times half of theta, right? That's from here. And then from here, it contributes the same amount of drag because it's a pull, right? And here the same, and here the same. So you have this multiplied by a factor of 4. Agree? That's the symmetric airfoil. On this airfoil, you don't have bottom contribution. You only have top contribution, so you have multiplied by 2. However, what's inside is 2 delta P, okay, times half chord, then times the entire theta, right? What you get here is delta P times C times theta. What you get here is 2 times delta P times C times theta. So you get twice the amount of drag with the same thickness, just by increasing camber. Okay, I mean the reason is this quadratic relationship of the drag component, right? Because when you change the slope, you not only change the delta pressure, you also change the angle of the action of the pressure. Okay, so you have a quadratic relationship of how the drag component due to pressure changes as you change the slope. And that nonlinearity makes it not as much of a good idea to have a highly cambered airfoil for supersonic flight. Right. I mean, just explaining intuitively, if you read Anderson's book, you actually have formulas, right, that tells you what's the contribution of the camber to the wave drag. But intuitively, it is the quadratic relationship of the drag to the slope that is making this a bad idea.